time for you to have to tell me anything, so you're automatically off the hook, but all right. So this guy here, real quick. What's the other way to write this?
The integral.
Good. Integral. Yeah, in here, there's hidden that a to b thing, so that's one reason why this is a better way to write the area. And this captures the idea that it's getting infinitesimally small, the widths. They have to, because they're going to fit an infinite number of rectangles in between a and b, so they got to be infinitesimally small bases. So that becomes dx when it gets really tiny. All right, you doing okay? Okay. So this, let's look at it this way. If I have a function and define it to be this, let me see if you guys understand this. All right, let me draw a picture that illustrates this. This is a weird function because as I change x, what am I actually changing?
The area under the function.
Yes, because I'm changing what?
The second.
The interval, right? So the interval that I want the area under the function. So that's why it changes the area. So what does this look like visually? I don't know. Oh, so now my function has got like the t-axis here, right? And this is the f of t. So I'm going from a to some point x, and here's my f of t. So this g of x represents the area there, right? That's what g of x represents. All right, let me stop there. That's nice. The visual kind of makes it hammer home. So this function is sort of like an area function. It's the area from a up to some point. You tell me how far you want me to go. I like it. And if the point you want me to go to is before a, it's going to come out negative. I don't know if you guys remember that. No, you're like, dude, right now, we don't know shit. All right. So here's what's kind of nifty. If I wanted to figure out what the derivative of this is, don't freak out. We're not going to do like really in-depth analysis of this. But what would the derivative mean in this case? What's the derivative mean just for a normal function? What's the derivative really mean? So if I'm at the point 1 and I know the derivative is here, it's like 3. What does that mean? In fact, yeah, say again?
The rate of change of the function.
Rate of change of the function over, so the rate of change of the outputs as I change the inputs, right? Mm-hmm. So if this slope here is 3, then I can say, well, 1 away from where I am now, wherever I am, this should go up roughly 3. And that's the whole idea behind the horrible trough problem and the stalactite problem and all those problems. If I let this much time go by, the derivative should be an estimate of how much it actually changes. Because that's what a derivative means. It means how much the function outputs change over some interval of x. That's what it means. Because that's what a slope means. Slope tells you if I change x by this much, the function is going to change by that much. Okay, maybe. You guys are like, sure. So here, what did I say this was a function basically representing what? Physical?
The area.
The area. It's like an area function, a cumulative area function from a to whatever. So I'm going to let x change by, my favorite thing to just let x change by, h. Right? Because then h, we're going to let h go to 0. Uh-oh. I want the slight little change, right?
So it's telling you the change in area over time?
I love it. So now it's going to represent a change in area per change in x. How much my area changes as I increase my interval a little bit. And I mean, when I say a little bit, I really, really mean a little bit. Right? All right. Maybe. So what I'm really looking at, don't freak out. This whole thing, remember this whole thing? All right. Physically, what is the top of that? Well, what can I complete up here on the picture that would represent? Because like you just said, what is it supposed to represent? A change in area. Because this is an area function, right? So it should be how much the area changes as I change the x.
So it's like the strip between.
I love it. It's this strip right there. It's the area of this strip. Okay, maybe. So if I change x a little bit, how much will the area change by? Whatever the area of this little strip is. Cool, I like it. So what is the area of that little strip? Well, how wide is it? H.
I'm so sorry to interrupt your lecture and train of thought. I believe that there is a textbook hopefully here, a calculus single variable.
Yeah, you're surrounded by them, but is it
That's
paperback or hard?
Claimed here. It's a paperback.
Okay.
Sir, you are a help.
Sure,
I'm
I
sorry
picked the book up.
You all have a great day.
Take care, man. All right. So that's the width of h. Is everybody cool with that? Of course it is, because that's how far apart x and x will take. How tall is that? Remember, this is way way exaggerated, because how far is this really? H is going to 0. So this is like that. It's like right on top of that, right? So how tall is it? Well, it's going to be this tall. How tall is that? What is that? What's this? Yeah, well, so what is it exactly? How tall is this? F of x. Right? What's f evaluated x? F of x. Isn't that how tall that is?
Yeah.
Alright. So g of x plus h minus g of x. Physically, that is the new area that I pick up. Right? Here's the old area. Here's the new total area. So the difference would be this little sliver. And let me make sure everybody understands. G of x is the area from a to x. What's g of x plus h? The area from a to x plus h. So what's the difference between them?
That
little sliver. So that equals, what's the area then if it's this tall and this wide?
F of x times h.
How tall is it? F of x. How wide is it? Now say it again what you said. Times h. Okay, sorry. I don't know if that's what you said. It sounded like you said f of x plus h. I'm like, shit. So then what does this become? What does it become? That goes there. So you get f of x. So the derivative of this, that's what we just calculated here, right?
Yeah.
The derivative of that is f. Now what's really important here, and you guys are still like, okay, but do you guys realize, isn't this the area under f?
Yes.
And when you take the derivative of it, you get f itself back. So what does that mean then? That means that if I take the antiderivative of both sides, don't I get g of x equals the antiderivative of f? Is that cool? Plus c, but who cares? I do, huh? But just an idea. So that means, and I know I've said this already, but now we've officially shown that g of x is this, which is the antiderivative. That's the first time we've been able to say this. The integral of a function is directly related to its antiderivative. So this is what's known as the, well, I'll show you exactly what it is, and then we'll, oh, I got plenty of time.
Why did the f of t turn to an f of x?
So, how do I say this? Well, I mean, for one thing, it didn't turn into it, right? It's just came out of the work. I mean, how tall is this sliver? F of x tall. So it didn't turn into it. It's just setting up what this represents and then doing the derivative made that come out. All right, so that by itself, right? So it's not, I just did the work that I needed to do to get what I wanted, which was the derivative of this. In doing that, it's not that the t became x. It's that since it was all about this location, that's what comes out at the end. It's all about that location. And what is that location? Anywhere I want it to be, right? Because x could be anything.
So like the f of t, like the whole function, and the f of x is like at a specific.
Yeah. This is sort of like this t is a dummy variable. Because what's the true variable for this function? X. So like this is a given function. It's got its own little variable. It's like, oh, that's cute. The real variable for me is x. It's the area under u. So I just care about how far I'm looking to get that area. So the real variable here is x. I like it. Maybe. So here's what, and you know what this is called? This is called the fundamental theorem of calculus, part 1. It's not as good as history of the world, I know.
37 plus.
Good to be the king. So here's what it says. It says that if g of x equals this, gather x, then g prime of x equals f of x. Which we still don't fully grasp the amazingness of, but we will soon, because we are not going to, until the final, we're not going to apply that limit definition of integration, the one that was up here. Sort of like we let go of limits for derivatives once we learn how to do the shortcuts, the same thing with this process here, right? We're going to come up now, I can evaluate integrals using its antiderivative, which hopefully will become easier and easier as we do more and more of them. See how much that's extra. So there's a part 2 to this, which is the part that's more practical. This is the idea that allows part 2 to exist. But part 2 sort of gives me a framework for how to attack any integral. I have to find its antiderivative first and then do something. So that's what we're going to work on next time.